From the Library of Congress in Washington, D.C.
Welcome everyone to this joint CENDI, FLIC, FAGI digitization workshop series. This is number 5. It's hard to believe that we've had 5 of these already. And I would call your attention to the information, as scant as it is, at the bottom of your program, which talks about the number 6 and 7. We will focus on a topic that actually came from many people who've attended the workshops before, and that is the issue of 508 compliance and digitization. So look for more information on the CENDI website and your listservs. Now, what I'd like to do is to introduce James Snyder. James is a digital media engineering, production, and project management specialist. His extensive experience includes television, film, radio, internet technologies, and covers the gamut from traditional analog to cutting-edge digital data, audio, and video technologies. His career in both commercial and non-commercial sectors spans over 30 years. Mr. Snyder currently serves as the Senior Systems Administrator for the Library of Congress's National, this is a mouthful, Audiovisual Conservation Center, located on the Packard Campus for audiovisual conservation in Culpeper, Virginia. And thank you, James, for coming so far. I know it's a trip. He's responsible for all the audio, video, and film preservation and digitization technologies, including long-term planning technology services to the United States Congress and Capitol Hill, as well as standards participation and interaction with media content producers. So with that kind of illustrious background, we look forward to hearing what James has to tell us about the archiving and preservation of moving images. Thank you, James. Welcome.
Thank you, Gail, and thank you everyone for coming today. This is quite a crowd, I must say. And I wish I could say that Biography was a spontaneous authorship of the folks here, but those were my own words that I wrote for a bio about 2 years ago, and it's odd hearing them being spoken. So thank you all for coming. It's great to be here, and it's great to talk about moving image archiving. And you may say to yourself, why are you using that term? Well, hopefully you will realize during the course of today that once you get into digital, it really doesn't matter if your source was video, or your source was film, or your source was electronic cinema. It's all moving image archiving. I'm also going to be talking a little bit about audio and some of the technologies behind this. One of the things that you should also be aware of, though, is that this is the first time I've given this particular concentration on this presentation. So if folks would like to give me feedback about what it did or didn't do for you, this particular concentration, I would appreciate it. A few items about myself. I won't go over these in detail because you can read my bio as well as I can. This workshop was adapted from a number of different seminars and workshops given over the years for many different organizations involving digital television and internet media. And again, I'll let you read that for your own aggrandizement. Our agenda for today is, first of all, I'm going to introduce you to what we're talking about. And then second, I'm going to walk you through the basics of analog moving images, whether those moving images be video or the moving images be film. And since in many cases your moving image also has audio attached, I'm going to make a couple of notes about audio. I'm not going to go in depth in audio, but some key notes about audio as well. I'm going to walk you through the basic concepts of digitization and also some basics of what born digital moving image content is. In other words, what does it really mean, and what are the different types? Physical media and files are the two basic categories there. A little bit on the evaluation of physical media, because this presentation I think may actually run over time. I only have a few slides on this, so if folks have suggestions on what they'd like to see in the future, if this is, or a version of this is given again, that would always be appreciated, but hopefully give you some highlights of how do you inspect your media and some of the issues involved. And also some notes on choosing an archival file format. I'm going to concentrate on the two main choices, which are either uncompressed or JPEG 2000 lossless. And the reason I'm going to concentrate mostly on JPEG 2000 lossless as a compressed choice is because that's what we've chosen here in the library, and I think the best example to show you what the decision-making choices are is to walk you through why we chose what we chose. There are other choices, of course, but there are some compelling reasons not necessarily to choose those, and I'll mention those as we go along. And then a little bit on the IT systems behind this, because when you get to files, you really are talking about IT-related systems. But you're not talking about just IT-related systems. One of the things that we've begun to learn as we've gotten into this really interesting adventure in large-scale digitization, at least for us, large-scale digitization, is that many of our requirements for our IT infrastructure are actually outstripping what enterprise-class IT was designed to do. And that's a fascinating adventure to realize that the systems designed for corporate IBM and Citibank and other areas like that actually don't match terribly well to what we're trying to do, and there'll be a few notes about that as well. I'm hoping that we'll get to the rest of these items, but there are 110 slides in this presentation, so we'll see. If we do get there, we're going to get to the end of the workflow, which is, of course, storage and how you choose storage and some of the issues in storage. Things like regular migrations, verifying your archive, whether or not to use cryptographic hash sums and what that really means. And then a few notes on the future of storage. Sometimes the future of storage is we'll see where the science goes, but we do have some choices now. They're not necessarily ideal, but we do have choices. For the most part, I'd appreciate if questions would remain for the end of the presentation. However, if something really occurs to you and you really got to know it in the middle, as long as we don't take too many of them, I'll be happy to take a question or two as we go along. I may have to move on at some point, so I hope you understand that if I don't answer your question in full in the middle of the presentation, hopefully we'll have some time at the end as well. So first of all, and by the way, I apologize, I have a head cold, or I'm coming off a head cold, so my voice is probably going to crack, and I'm definitely going to have to use some water and sneeze a couple of times during the presentation. So if that happens, like now, I apologize. So let's go ahead and move into this. I'm not going to go through this in a great deal of detail, but basically, where do we start when we talk about video? Well, video started off with black and white video systems. The very first one to go on the air for broadcasting was the UK 405 line system in 1936. They actually predated the American system, which was the NTSC system. NTSC, for those of you who will be asked this trivia question if you run into me in the future, stands for the National Television System Committee. Many people get that wrong, and I just enjoy bringing that out on the odd occasion. There was also a 819 line system in France, which began in 1947. 819 line, that's actually more than the 720 line system that we have for high definition today. It did not last terribly long, and there are very few recordings of it, but it did exist. Color video started with the color NTSC system in 1951, which was called line sequential, and it was a beautiful color system, and it gave great pictures, and it was also incompatible with all the black and white systems. So it was not terribly popular, and for some machinations which were both political and technical, it was rescinded in 1953, and what's known as the RCA compatible color system was adopted in 1954, which allowed both black and white and color sets to operate on the same channels with the same standard without too many issues. If you want to know what the issues of composite are, I will be happy to walk you through that. The one thing that I will not be sorry to see go will be NTSC. I'm very glad NTSC broadcasting is gone, but there are a whole bunch of problems, a few of which I'm going to mention as we go along, that came up because of NTSC color. The only way to record a video up until roughly 1956 was the kinescope, which is film recording of video. There was no electronic way to record video until 1956. And even then, film recording of video continued until The Tonight Show transferred to NBC Burbank in 1971. There were still some kinescopes being made. And in fact, if you've ever heard the legendary story of how The Tonight Show, the first 6 years of The Tonight Show are lost because somebody went into a storage closet at NBC New York and said, all those shelves, yeah, get rid of them. That was the first 6 years of The Tonight Show that got erased. And so the only copies of The Tonight Show, the first 6 years of The Tonight Show that you will see will be the kinescopes that were created for distribution to television stations. There are no video copies. Videotape was created by Ampex in 1956 and premiered at the NAB convention in 1956 and was first used in production from CBS Television City for time-delayed West Coast broadcasting in November of 1956. It started gaining widespread adoption in 1957 and into 1958. One of the things, if any of you deal with early color videotapes, that you will need to be aware of is if you have a color 2-inch videotape before 1962, it is most likely the NBC or RCA color variant that requires special decoding circuitry, and that's why I mention it here. We actually have some of those tapes. And may I say they're a royal pain in the neck to deal with, but then quad is a royal pain in the neck anyway. The first standardized quad VTR was the VR2000B in 1962, and that's when both RCA and Ampex got together and agreed how to do color for 2-inch videotape. PAL and CCAM were the analog systems for the rest of the world. PAL stands for phase alternating line. CCAM stands for sequential color avec mémoire. That was invented by the French because Charles de Gaulle decided that he wanted to create a consumer electronics industry in France. Gee, how'd that go for him? And it turned out to be a great way for the communist countries to, prevent many broadcasts in PAL and NTSC from being received in their country because PAL and NTSC broadcasts were not completely compatible with CCAM. So most of the former Soviet and communist states are all former CCAM states as well. So they have a great deal of CCAM material. The first affordable VTRs were 2-inch, and affordable is in quotes here because they were still, tens of thousands of dollars as opposed to hundreds of thousands of dollars. They were used for movies on airplanes. There were different VTRs created that were incompatible with each other and sometimes were incompatible with themselves, where you could record a video on one machine by Sony and take it to exactly that same model number and play it on that machine, and it actually wouldn't play terribly well. That's what we call interchange issues. So if you deal with any 1/2-inch or 1-inch open reel videotape before roughly 1969, you're probably going to run into some compatibility issues. Color VTRs first appeared in the early 1960s, but later on we had some of the 1/2-inch and 1-inch VTRs start to appear. The most common one before the 3/4-inch VTR was the 1/2-inch EIAJ format. EIAJ, of course, stands for the Electronic Industries of Japan. It started off as a black and white format, but became a color format in the early 1970s, basically when consumer quality color cameras became available. There's also a cassette version, which is very rare, but if you take the tape out, or if you have a machine that'll play it, it's basically the EIAJ2 color standard, so it's exactly the same signal on the tape. U-matic came along in 1971, and one of the key technology developments in history is electronic news gathering, which started roughly in 1973 at WCAU in Philadelphia, and gained wide acceptance after the invention of the time-based corrector in 1973. So that's when you're going to start to see a great proliferation in 3/4-inch video cassettes, because that could be used for news gathering. 1-inch professional VTRs, in other words, that could give you the quality of 2-inch videotape, but with a smaller size and a much lower cost, were standardized in 1974 and 75. There's the Type B, which was used mostly overseas, and there was Type C that was introduced by Ampex and Sony, and they did not necessarily go willingly. Basically, the vice president for ABC News and Sports got them together in 1975 and said, I want you two to cooperate with each other and come up with a standardized VTR that can do slow motion and noiseless still frame. I have $150 million to spend. Go. And they groused about it and they bitched about it and they finally got together and they invented the Type C VTR. So does anybody remember Warner Wolf from Washington Television? Raise your hands. Warner Wolf. Warner Wolf is the reason the Type C VTR exists. Because when he went from WTOP television to ABC Sports, he said, I want a better way of doing sports on video, and that's when the head of ABC Sports went to Ampex and Sony. So Warner Wolf, you have to thank for the 1-inch Type C VTR. Oops. Now, digital started in the 70s with little tiny islands inside of individual pieces of equipment. Time-based correctors, frame synchronizers, some digital graphics, some video effects generators. There were some, the distribution both in plant and broadcast was still composite. However, one thing of note, in 1974, NHK and Sony demonstrated the first practical high-definition television system in Japan. So high definition has been around a lot longer than people realize. Now, yes? For those of you who are listening to me on the web, you may be hearing me in the Kermit the Frog mode, because that's basically the way my voice is now. I will try and speak a little bit better. Not quite sure what that means, but I hope you'll bear with me. Some of the key technical developments is the analog component video standard was set by the SMPTE in 1978. So if you've heard of RGB and YPBPR, that is when those became standardized. The digital video sampling standard, which was CCIR 601, or what you may know as 601 video, was set in 1982. One of the key things to remember about CCIR 601 is that it was 8-bit video, not 10-bit video, and I'll get into why that's important as we go along. And then the serial digital interface, what we call SDI or SMPTE 259, which is the standard for SD digital video, was set in 1989, and that was when the standard was updated to include 10-bit video. And the reason they included 10 bits instead of 8 bits, or just 8 bits, was to eliminate the visible contouring in colors. If you want to know why 8-bit is worse than 10-bit, imagine a blue sky. And if you take a very close look at the blue sky, and especially if you look at the electronic values of the color blue in the signal, they vary slightly from one side of the screen to the other. There are different shades of blue. And when you use 8-bit sampling, you get visible contouring between shades of blue because there aren't enough bits to represent a nice smooth contour across the entire screen. That's why we have 10-bit video instead of 8-bit video. And I talked to a gentleman by the name of Merrill Weiss, who is still active in the industry today, who was a part of the standardization effort back in the mid-1980s, and he said, the moment we built the first digital VTR that did 8-bit video, and we took it outside and recorded video onto it of, this beautiful spring day, we were like, holy crap, 8 bits is not going to be enough, because apparently they were visible contour lines after millions of dollars of investment and years of effort. So at that point they realized that 10-bit was going to be the minimum to do really good production quality video. That's why we have that difference. As we move into the 80s, we see the proliferation of different both analog and digital formats. One of the key differences in these formats is you have analog component formats starting to appear, like the M format, which is different from the M2 format, but it's related to it, the Sony Betacam format. And then you have your first digital VTRs, the D1, which was a 19 millimeter, which was the new name for 3/4 inch, because apparently 3/4 inch was a bad word back then. So they called it 19 millimeter. That was 8-bit digital VTR based on the CCIR 601 standard. And then there was the D2 machine, which again was a 19 millimeter, but it used, or it could digitize composite video directly. Composite video is, of course, analog video, NTSC, PAL, and CCAM, as we know it. And that was a major upgrade in general, because it allowed you to get as perfect an analog signal as a digitally captured signal as possible. And it did that by using what's called 4x subcarrier sampling. One of the key things about D1 VTRs is I've run into several archives around the world who actually spent a lot of money converting their analog videotapes to D1 tapes. And one of the questions they have is that good enough? Can I go ahead and just convert my D1s into files or whatever? And I said, well, you can. You will certainly get good-looking video, but be aware if there was better quality in your analog videotapes, I would actually, and you can still get to your analog videotapes, I would suggest you go back and you remigrate your original analogs, because D1 is 8-bit video and you will get visible contouring in the video for things like blue skies and stuff like that. So if you have the choice, because obviously that's also a cost-related issue, if you have a choice, be aware that that's one of the issues with D1. Now, if the material was created as a native D1 material, clearly you can't go back and change that. It is what it is, and you can go ahead and migrate that. A couple of other developments. The first analog HDTV video recorder came along in 1984. The effort to create what is now our digital television standard in the United States began in 1986, and the first digital broadcast quality HD recorders were in 1988. The MPEG standard, which many of us know so well and love so vociferously, came along in 1994. The key technical innovation is it was the first high-quality but lossy compression system, but it was the first high-quality compression system. If anybody remembers MPEG-1, you know what I mean by high quality. It was also the first standard that allowed full resolution SD and in fact HD to be created with compression, of course, and it was adopted by both the American and the European digital television standardization folks. One of the key problems, though, with MPEG, and this was mostly because of the throughputs available at the time, was there was no lossless compression scheme. And so if you ask why did JPEG 2000 do it but MPEG 2 didn't, it wasn't because they didn't see the future, it's because there were technical interference. There was a technical inability to be able to handle lossless encoding at that point. There were more digital VTRs that came along. Digital video servers were debuting in the 90s. Computer-based nonlinear editing was coming to the fore. And so this is where file-based workflows had begun to develop. That's one of the key points that we're going to be going through today is we're switching. If you're doing migrations, you are switching from a linear-based workflow to a file-based workflow. And this is where that change started to happen. The HD digital standard was set in '96, and along came some digital VTRs and some high-def VTRs to match that. This is also the first appearance of file-based production and transmission systems where digital video servers were becoming widely available, and a computer-based nonlinear editing and post-production had really become fairly widespread. The US DTV standard was set officially on July 1st, 1996, and the first TV station went on the air on July 1st of 1996, and that was WRAL in Raleigh. The first one that actually was running programs instead of just random bits was a station called WHD-TV, if you've ever heard of the model HD-TV station, that was it, on July 7th, 1996, and I'm very pleased to say that I was there when the switch was turned on and I pressed play on the VTR because I had this much of a role in it. But I was there, and that was one of those moments where you realize that, maybe you weren't changing history, but you were a part of a group that was changing history, and that was actually kind of cool. And now that the transition is over, the transition to digital was completed about a year and a half ago, it's interesting to go back and talk to the folks from that era about what we were thinking and what we said at the time, whether or not we were prescient or not. It's one of those interesting conversations one can have. In the 2000s, the JPEG 2000 standard was adopted in the year 2000. That's why it's called JPEG 2000. It was the first compression standard that allowed you to do lossless compression. And by lossless, we mean truly lossless. Basically, if you put it through an encode and then you decode it again, there is no documentable difference between the two of them. They are mathematically lossless. Unlike MPEG, where even if you do a high-quality MPEG-2 or MPEG-4, a high bitrate MPEG-2 or MPEG-4, there will be visible, sometimes not visible, but documentable artifacts inside of the video, and that's because that is a lossy compression scheme, which means you are throwing away parts of the original signal. The key part about MPEG and many of the other compression schemes is they are what's known as visually lossless. That means that a first generation encode, the normal human eye should not be able to see the difference between that and the original video. That doesn't mean there isn't a difference between that and the original video. When you go to the second generation, things start to come out pretty much immediately. That's the difference between the two. One of the key developments in the 2000s as well is we start having file-based acquisition formats. In the professional domain, we have XDCAM. In both the professional and the consumer domain, we have AVC HD. All of these create files either on solid-state media or on optical media like Blu-ray discs. And that's one of the key technological developments of the 2000s is file-based workflows have made it all the way to the point of acquisition, all the way to the camera. And in fact, if you take a look at my camera that I'm recording my presentation with here in the back, that is an AVC HD camera. And basically I have a little thumb thing that I pull out, a little chip that I can put into my computer, and I have a copy of my presentation. Imagine doing that with tape. You can't. You have to feed it into your computer to be able to do anything with it. So file-based workflows have made it all the way not only to the point of acquisition in professional media, but the point of acquisition in personal media as well. And that's a major change in how things occur within personal media. A few notes on audio development, not too much because obviously this is not an audio presentation. Digital audio processing islands, just like with video, started in the 1970s. Things like digital delays, reverberation units, digital audio effects. Stereo became common in the 1980s, and as time went on, you started getting more toolkits for the creation and the manipulation of digital audio, like audio mixers, audio tape recorders, hard disk recording, again, which is file-based workflows again. The audio interconnection standard, the AES standard, came along in 1992. And of course, the MP3 was created. That is the MPEG standard for high-quality audio, but at very high compressed rates. Now, for some of us who actually enjoy high-quality audio, we can make an argument about whether or not it's high quality, but I'll leave that for another day. Any questions? Okay. Let's keep going. First of all, let's take a look at the basics of analog moving images. Basically, any signal that you have, any signal in the world, is one of three things when it comes to transmitting and recording. It is a change in voltage, it is a change in light level, or it is a change in radio frequency. Everything in the world is some form of one of those three or a combination of the three. Everything. So keep that in mind. In the case of video, you have three channels, three color channels. They start off as red, green, and blue in color. And you have a voltage level varying from the very darkest color to the very lightest color. In the case of black and white, it would have been from black, whatever the definition of black was, to whatever the definition of white was. And of course, we have scan lines. And so every time you scan a line, you have a waveform, and then you go back to the beginning of the next line, and you scan the next waveform. One of the key things that I do need to bring to your attention is the difference in scanning rasters. Now, for example, our 525 and 625 line standards were both interlace, but we also have what's known as progressive, like this screen that I'm using here for the computer. This is a progressively scanned monitor. All flat panels, if you have a flat panel at home, how many people have a flat panel at home? Every single flat panel known to man, maybe with one or two exceptions, is progressively scanned. So then you have to ask yourself, well, how do we get from interlace video to progressive video in these things? Well, that's called a scan converter, and sometimes that does a good job and you don't see the effects of the scan conversion. Sometimes it does a bad job and you see the effects of the scan conversion. So if you sometimes wonder why the quality of the video on your TV set at home may not be exactly what you expected it to be, part of it may actually be your own TV screen. Part of it may be compression, part of it may be a couple of other things. The interesting part about this business is it's kind of a whack-a-mole these days. You don't quite know exactly what everything is. If you get to know all the different types of artifacts, you can make really educated guesses. But in the end, unless you have some really good test signals, you don't know for sure. And that's actually been one of the great, changes in how we do video and how we do moving image, is being able to figure out what those things are. The conversion from analog to digital is also the Engineers Full Employment Act. That's one of the nice things about it. So the difference between progressive scan and interlace is progressive starts at the top and progressively scans each line in sequence, 1, 2, 3, 4, 5, 6, all the way to the end of the raster. Whereas with interlace, it does all the odd lines first, 1, 3, 5, 7, 9, and then it goes back and it does all the even lines, 2, 4, 6, 8, 10. Can anybody tell me why they would do that? Why would they design a system to do it that way? Why wouldn't they do progressive from the beginning?
I think for television, you could see it. If you're only updating the screen, is the question of the persistence on the screen and seeing a flicker.
Why is that bad? Why is that bad?
Distracting?
Yes. Granted as fact, absolutely. In essence, though, what I was aiming for is it's a form of temporal compression. In other words, you know that you can either double your frame rate to get rid of the flicker, or you can interlace and fool the eye into thinking that it's seeing 60 frames per second when in fact it's seeing 30. So back in the days of vacuum tubes where scan rates couldn't be terribly high, it was one of the ways to make people think they're seeing, you know, high frame rate when in fact they're not. So close, very close. Okay. One concept that you should at least become slightly familiar with is colorimetry. The reason I say this is there are different types of color that exist. There's analog color, there's digital color, there's different standards for color. If you look at the SDI standard, that's what's known as 601 color. If you look at HD video, that's what's known as Rec 709 color. And that's because the color values, depending on the resolution, or depending on the standard actually, not on the resolution, the color space can actually be different. Film has different color space than video does. Electronic imaging has different color space than video or film does. And so one of the things you need to be aware of is when you're talking color, if you're talking RGB, if you're talking YPBPR, what are you really talking about? You know, what color space are you talking about? And so one of the great challenges, especially as we've converted to digital in broadcasting and production, and of course we're going to face this as folks who need to preserve this material, is saying, okay, when you do an analog to digital conversion, are you actually doing the right color space? And that's a concept that I'd like to get you at least thinking about. What color space are we looking at? And so when we talk about colorimetry, in analog, we're talking about the color values that are valid within a given definition. A definition like the SMPTE 259 SD definition, or the SMPTE 292 HD definition, or certain color stocks like ectochrome. What color definitions are you actually thinking of? And of course, those voltage definitions in analog map to digital values in digital. And if you need to convert from one color space to another, what does that really mean? Because many people say, well, you know, if I have a PAL videotape, can't I just convert it to NTSC and then convert it to SDI and then convert it into a file? Well, yes, you could. If your goal, though, is to have what actually looks like the original material, I can tell you right now, that's not going to look like the original material. It's not going to look close. And one of the reasons why is the differences in colorimetry. As a concept, one thing I'd like to get you familiar with, if you're not already, is we've got two types of component video. We've got RGB, which is full resolution, as much information as you can capture from the original capture device. But we've also got what's known as YPBPR, which again is a way of compressing or not representing as many values because back in the day we didn't have enough throughput and speed to be able to handle RGB all the way around the world, including transmission. And so if you see YPBPR, what you're actually talking about is a monochrome signal, Y, followed by two chroma signals, which are PB and PR. And those are known as color difference signals. So one of the things you're going to hear me say, and one of the things if we ever talk about stuff face to face, if you ever use the word component for YPBPR, I will correct you. That is component color difference. Component is RGB, because those are the original three components that video are produced in. And the color difference signals, which were R minus Y and B minus Y for simplicity's sake, are represented as PB and PR. So if you ever see Y, R minus Y, B minus Y, YPBPR means the same thing. Those are two different terms for the same thing. In NTSC, these are processed to become what's known as the I and Q signals. So if you ever look at a vector scope, you will see two 90-degree angle offset vectors, usually labeled I and Q. That is where the color information for NTSC is actually modulated. That's where it's actually carried in the analog signal. In PAL, they're known as U and V. Now, one of the things that I need to say is many people around the world use YUV to mean YPBPR. They are not the same thing. So if you mean component color difference, say YPBPR. If you mean PAL component color difference that's modulated as an analog signal, that is YUV. This is what an analog waveform looks like as a drawing, and this is what it looks like in reality. So if you've ever seen a scope before, you're familiar with this. If you haven't seen a scope before, this is one television line of color bars, and we'll see the actual video as we go along. The left-hand side, you'll notice there are two things that look roughly the same next to each other. The left-hand one is field 1, which is all the, which is the odd line. The right-hand one is field 2, and in this case, I've put the color information, I've superimposed the color information over it so that we could see what the black and white version of the picture looks like and what the color version of the picture looks like. Now you may say, well, why do I care about this? Because these kind of test signals and this type of monitor is what tells you how good the signal is that you're, first of all, recovering off the tape, and second of all, that you're putting into your analog to digital converters. And remember, when it comes to analog to digital conversion, garbage in is garbage out. And in many cases, the garbage will also be digital garbage, because if the analog signal does not fit certain parameters, the analog to digital converters will start injecting unintended artifacts into the digital picture, like green lines and pops and clicks in the audio. That's a bad audio to digital or analog to digital conversion. The most common video formats are 525 and 625, which are the legacy formats, of course. However, in digital, they're known as 486 or 480 and 576. And they are 720 pixels by so many lines. And so you'll notice the nomenclature for this presentation, in fact, the most common nomenclature in the industry is how many horizontal pixels by how many vertical lines. So 720 pixels by 486 vertical lines, and then how many frames per second is your video being reproduced at. In the case of NTSC, it's 29.97. In the case of PAL and CCAM, with one exception, it is 25 frames per second. Can anybody tell me the one exception to PAL and CCAM where it is not 25 frames per second? Your test for the day. Well, one of many. Okay, in Brazil, in their infinite wisdom, Brazil decided to adopt 525 lines, but PAL color. So they actually do 29.97, but PAL color transmission. That makes for some interesting videotapes when you look at stuff coming out of South America. In the case of HD, we've got 720p. If you've heard of 720p, what that really means is 1280 pixels, horizontal pixels, by 720 vertical lines. And you can have any of a number of different frame rates, but the most common frame rate is 5994. If you watch ABC television or ESPN in HD or Fox television, that is 720p 5994. In the case of 1080 line HD, it is 1920 horizontal pixels by 1080 vertical lines. And again, it can have different frame rates. The most common is 29.97. However, both 5994 and 60 frame per second video is in development, and we may see that in the not too distant future. One of the things that I need to bring to your attention is there's the dreaded 1080i60. This is a Sony nomenclature that was created in the mid-1990s by a gentleman named Larry Thorpe. And I love Larry dearly. He's one of the nicest Irishmen I've ever met in my life, but he was the one who came up with 1080i60. And one of the problems with, and Sony adopted it, he was at Sony at the time, and Sony adopted it, and it's become standard nomenclature throughout the industry. There is no such thing as 1080i60. It does not exist. So be careful when you're talking about 1080i60, when you have your television screen up and it says 1080i60 as the standard in the lower left-hand corner. It's not. It's 1080i 2997. You will also notice many professional and consumer documents say 1080i60. Doesn't exist. Not a format. It's a Sonyism. So keep that in mind. It's a misnomer. Can anybody tell me why we have these odd numbers? 29.97, 59.94, 23.98. Anybody want to take a stab at that? Why would we have those weird numbers? Ooh, nobody. Okay. Well, it's pretty straightforward. Back in the days when compatible color came along, and when I say compatible color, I mean NTSC color, what they had to do, because they wanted to make it backwards compatible with black and white, is they couldn't really fit the color signal into the black and white signal terribly easily. So they tried all sorts of different ways of interleaving it and doing all sorts of different things. But in the end, what they did was, because again, this was the vacuum tube era, they slowed down the video slightly by 1/1000th of a second. And so in that way, they could interleave the color and the black and white information pretty well together, and it worked pretty well. And so that's why we have these odd numbers, because instead of being 30, the original black and white system was 30. So if you take 30 and you divide it by 1.001, 1/1000th of 30, you get 29.97. Now, needless to say, that has made for, as in the digital era, made for some really interesting mathematics. And in fact, when you start talking time code, this is where our heads start to hurt. When you have time code on the tape, do you have drop time code or non-drop time code? If you want to know more about that, ask. I won't go into it too much during this presentation. And for the purposes of this presentation, you will notice that I stands for interlace, P stands for progressive, and so digitized NTSC is 486i 2997. 720 line video is 720p 60 or 720p 5994, and then 1080 line video is 1080i 2997, and so on. You will notice that there are different forms or different nomenclatures that they use. Some of them use a slash. Some of them use different, orientations for how to do it. I find that just saying 720p 60 or 720p 5994 as a term, it's straightforward and it's clean, and you don't have slashes, and it's pretty straightforward. I prefer it that way. So when you're making digitizing decisions, if the goal is the best quality, you need to keep a couple of different things in mind. Now, one of the things I'm very well aware is there's a balancing act, especially for those of us who are not the Library of Congress. There is a balancing act between the best quality and what we can actually afford to do. So keep in mind, this is best quality. That doesn't mean you're necessarily going to be able to afford to get there. And that, for the most part, is okay. There are expediencies. Do you save the material, or do you try and spend gobs of money to get the best you actually can? Sometimes you don't have to spend gobs of money. Sometimes you do. So it's a balancing act between how do I do the best that I can and get the original material versus how do I actually save it and I only have $10,000 to do it. Because for many of us, that's a real decision-making process. And so no harm, no foul on making those types of decisions. That's an expediency decision, and that's fine. But if you want to maintain the original quality, 10-bit sampling must be used for exactly the reason that I mentioned before. It's 4 times the accuracy, because it's a binary number. It's 4 times the accuracy of 8-bit video. It's not 2 bits more, it's 4 times the accuracy. And I'll go into that as we go along. A high-quality analog to digital converter must be used that separates the color from the black and white as cleanly as possible. However, be aware, you will never do it completely cleanly. You will always notice artifacts that came from the fact that the color and the black and white were interleaved with each other. If you ever look at an analog television screen, I'm going to destroy your way to watch television now, you poor things. If you want to see the artifact that tells you that this is an analog signal or was an analog signal originally, even though it may be digital now. If you take a look at things like news coverage, where you have an anchor with a box over their shoulder, the vertical edges of those boxes will appear to have little dots going from bottom to top. That is an artifact of the interleaving of color in black and white, because those dots are the Luma decoder incorrectly decoding color information as luminance information and vice versa. That's one of the key ways to tell something that has been analog video, and you cannot get rid of it. You can lower the impact of the dots, you can make them as unobtrusive as possible, but they will always be there. So that's also a reason to never ever, if you've been in the digital domain, to never ever go back to analog and then go back to digital. Don't ever go to that composite step, whether it be NTSC or PAL, because those artifacts are injected and they cannot be taken out. So just be aware, when you digitize your analog video, it will not look like perfect digital video. It will always look like a really good version of analog video. So when you're inspecting your media, what do you look for? Well, with tape, you need to watch out for sticky shed. Sticky shed, of course, is a myriad of problems that basically revolve around something being on the surface of the tape that first of all makes it stick, and second of all makes it shed the oxide and pieces of the tape. One of the key factors in whether or not you're going to deal with sticky shed, first of all, for the most common format out there, which is one of the most common formats, which is 3/4 inch. Both Scotch and Ampex debuted their broadcast quality 3/4 inch tapes in 1978. And so that's the dividing line, the color or the quality line for 3/4 inch videotape. Anything before 1978 has a lot more incidents of sticky shed, tape leader splices that fail, mechanical failures, and so forth. One of the key things I can recommend is, and this is a big if you can afford a tape inspector, buy it. If you can afford a tape cleaner, buy it. However, I will warn you right now, they are not cheap. They go from roughly $15,000 for the ones that may or may not ruin your tape simply by processing them, to $40,000 and $50,000. So they're the cost of a VTR, a brand new VTR. But if you can afford it, the best thing I can tell you is go ahead and get a tape inspector and a tape cleaner. The only proven treatment at this point for sticky shed is baking, which, as many of you probably already know, is heating the tape in an oven to approximately 130 degrees for several hours. Basically, what the stickiness is on the surface of the tape is something is coming out of the tape that makes it sticky. And the reason it's coming out of the tape, or at least we believe the primary reason it's coming out of the tape, is because of hydrolysis. In other words, the tape is not a static device. It absorbs and lets off water. And as part of that absorption of water, it creates things on the surface of the tape. The only way to really get rid of it at this point is to bake the tape. The problem is it does not permanently stop the condition. There is some evidence that it may actually make the condition worse, where if you have to go back and bake it again, it'll actually, or if you go back to the tape again, it'll have actually made the condition worse. One of the things that we're studying right now is exactly what is this problem? What is sticky shed and what are we dealing with? And we're fairly early in this process. We don't have all the answers yet. And so as time goes on, hopefully we'll get there. So use baking with great caution. There's a good chance that you may damage or destroy your tape. So always assume if you have to bake a tape that you will get one chance to copy it, and one chance only. You may get more. It's quite possible you'll get more, but you may get it once. I've had tapes where we've put the tape into the VTR after baking it, and a little cloud of brown comes off of the tape heads, and the inside of the VTR, by the time the tape is over, is covered in oxide because it is just shedding it all over the place. To a certain extent, that may have been the original damage to the tape, or the aging of the tape, the natural process of the tape. That may have been baking. One of our issues is we don't know exactly where that dividing line is, and we're working on finding out more about that. So is there something better? Who knows? We're looking at a number of different things, storage in low humidity for long periods, treatment in a low humidity chamber with an active dry airflow for shorter periods. Can we adapt our playback devices to mitigate sticky shed, like cooling of the head stacks at the point of contact? This is all speculative right now. We don't know if this would do anything better. We're trying to do the homework to figure this out because clearly this is an exceedingly difficult problem, so stay tuned. One of the sobering aspects of our collection down at Culpeper is we have, needless to say, millions of items in our collection, but 130,000 of those items are 2-inch quad videotapes. And those videotapes are many of the seminal works in both public and commercial television, including almost the entire production run and the only known copies of Laugh-In and several other television programs from National Educational Television and PBS. And one of the problems we're running into is the Scotch 400 series videotape has an exceedingly bad sticky shed problem. And the problem is most of the tapes, starting in roughly 1972, are 400 series tapes. So we've got a really serious problem and we've got to deal with it. In the case of discs, you can get a degradation of the reflective layer. When you look at a disc and you see silver or gold, that is a reflective layer that reflects the laser light that is reading your disc. And so in the case of Laserdisc, which is an analog recording but on an optical disc, you need to watch out for disc rot, which is the actual reflective surface has started to go. If you see things, or if you play a Laserdisc suffering from disc rot, you will notice that there are white and black sparklies on the screen, not unlike analog television back in the day when you had an antenna. Those cannot be gotten rid of. They're there, and they're there for good, so be aware of that. Also be aware that many laser discs are 2 layers that are glued together. That glue may also be going. It may also be causing the reflective layer to be lost. In the case of CED, which was known as RCA Selectivision, that is a physical disc encased in a square plastic case. Do not, under any circumstances, open the case or touch the disc because you will permanently damage the recording. The only thing you need to make sure is the case okay? Is there a way that we can still play this disc? In the case of video CD and DVD, the pressed discs, the commercially pressed discs, which are colored usually either silver or gold, you can inspect the surface for any kind of data rot or any kind of surface rot. But burnable discs, which are basically dye layers that have had information pressed in them, our procedure is we copy them as soon as possible. In other words, we are turning them into ISO images, either CD standard or DVD standard ISO images. They are not aging terribly well. We've got 10-year-old discs that we can't read anymore. And that's content that may be gone for good if that was the only copy that was ever created. Any questions? Yeah.
I want to go back to your previous statement on CDs and DVDs. Am I to understand that burnable media, in your experience, has a shorter time frame than media that has been commercially produced and replicated?
Yes.
And again, why the difference, and how much more time do you attribute to the commercial media?
The reason is there's a fundamentally different design between the 2 types of discs. In the case of commercially pressed discs, whether they be CDs or DVDs, you have the plastic or the polycarbonate that the bits are actually pressed into. And then you have a reflective layer, which is metal, usually aluminum or some form of gold, sprayed on the disc that makes those bits or those depressions in the plastic make them visible to the layer. In other words, the system can see the difference between a 1 and a 0, if you will. In the case of burnable discs, that's a dye layer. And just as with color film that goes red within 5 years, any dye layer has a problem with going bad over time. It changes physically over time. It changes more if you leave it in heated areas. It changes less if you keep them cool. But the fact is it's going to change over time. And just as with any kind of, all-in-one dye-based color film system, you cannot stop those films from going red within 5 to 10 years. In the case of dye layer optical discs, it really depends on the quality of the manufacturing, on the quality of the dye layer, sometimes on individual production runs within the same manufacturer. There are differences between all different sorts, but given that we've seen such a wide range of quality differences in the burnable discs, our policy is as soon as we can get in front of what we already have in our collection, we're going to rip them, if you will, to ISO images as soon as we can when they come in the door, because we don't know whether or not that disc is going to survive 10 years or 2 years or maybe even 6 months, because we don't know what environmental conditions it came through before it came to us or what the quality of manufacturing was. And so our faith in the long-term ability of die layer burnable discs, the longevity, we don't have a great deal of faith in them. So until someone can show us something better, we're going to be cautious. Yes, Kate?
Can you just quickly talk about this low humidity study that you're doing, the treatments? Is that just internal to Culpeper, or are you working with some different?
Actually, we're not doing the work at all. And in fact, part of what I'm going to be doing later today is talking with the Preservation Directorate about this. But there have been some folks out there, and one of them is a gentleman in Philadelphia, and since I haven't asked him if it's okay to release his name, I won't. But there's a gent in Philadelphia who specifically has stored sticky shed tapes in a low humidity environment, and his on the ground experience is that has helped mitigate sticky shed. So that's an area that we're going to take a look at as time goes on, whether it be us in Culpeper or it be, you know, others that we work with. We're going to take a good hard look at that, because it actually kind of makes sense. If you treat things in a low humidity or even a close to no humidity environment, it may do the same thing as heating. And so if we're storing all of this media in these vaults anyway, why not store them in low humidity vaults? I mean, conceptually, store them in low humidity vaults, whereas we don't have to do something which we know causes problems, which is baking. Because basically that's what baking does. It's driving off the water. Does that answer your question?
It does.
Okay.
My not so secret agenda is let us know, James, because at the National Archives we might want to work with you on.
As soon as I know something, I will be happy to have that conversation with you. Yes?
Hi, for the purposes of the folks attending remotely, which is about 100, could we possibly repeat the question?
Oh, sure.
So that they have a context of
Absolutely.
answering?
I keep forgetting. The immediate previous question was Kate Murray from the National Archives asking about the low humidity study, and hopefully I answered that well enough. And then the question before that, which was about burnable optical discs, basically involved what's the difference between commercially pressed optical discs and burnable optical discs, and that of course is the dye layer versus the reflective layer. Any other questions? Okay, let's go on to motion picture film. The most common formats, and again, for those of you who are already familiar with this, excuse my repeating anything, the most common formats are 35 millimeter, which is still used in many motion picture theaters around, or most motion picture theaters around the world. There's also a variant of 35 millimeter known as Super 35, which is a camera negative and post-production format where the extra space that usually is taken up by the optical soundtrack is used for actual picture acquisition. So that there's actually a wider frame on the film. There's 16 millimeter, which has been a very common distribution format for a whole bunch of different uses. It's been very common for educational and instructional formats, industrial training, schools, and the like. It was used widely for television news acquisition and documentary production, including network television documentary production. Much of the 60 Minutes archive is on 16 millimeter film before they started using videotape in the 90s. Sometimes it comes with magnetic stripes on it for sync sound on the side, so you can actually record sound on the film in the field. It was a very common kinescope format. In fact, many of the Tonight Show films are 16 millimeter films, and many of the kinescopes that you see in collections or God help us, you see on eBay. Those are all 16 millimeter format films. It was the most common distribution format for television stations before the mid-1960s, when all television stations were finally tied together by landlines and microwaves. Most television stations outside of the top 30 markets were not tied together with direct transmission before the mid-1960s, and the only way they got their network programs was on 16 millimeter film. And then there's also a variant of 16 called Super 16, which again is a camera negative format where you can shoot a larger image to gain a little bit more quality, and it takes up the space that normally would be taken up by the optical soundtrack in 16 millimeter. There's 8 millimeter, which was designed as a consumer format and sometimes was 16 millimeter split in double perf split in half. Sometimes it was produced as 8 millimeter. There was also a variant that came along in the 60s called Super 8, which was a consumer format where it had actually smaller sprocket holes than 8 millimeter, which permitted more picture area to be recorded onto the film. And then there's 70 millimeter, which was a very high quality distribution and production format from the 1930s into the 1990s. Some uncommon formats just to note, things like 9.5 millimeter, 17.5 millimeter, which was 35 millimeter split in half, 28 millimeter, and 65 millimeter, which usually was a camera original negative shot for 70 millimeter distribution. In other words, if you take off that extra space on 70 millimeter that's used by the magnetic stripes for the soundtrack, that's basically 65 millimeter film. And so they didn't use the wider film for actual camera production. For film, resolution is usually measured in line pairs per millimeter, and that's roughly equivalent to what we think of as video lines of resolution. It's sometimes expressed as line pairs per picture height so that you can make a comparison between your video resolution or your electronic imaging resolution, if you will, and the film resolution. And that depends on many factors. The actual resolution on the film depends on many factors. How the emulsion was made, how the film was shot, because the quality of the lenses in front of the camera actually has a demonstrable effect on the resolution that actually makes it onto film. How the film was processed. Was it a mass-produced copy? Because mass-produced copies, which were done very, very quickly on contact printers that would run at hundreds, if not thousands of feet per minute, have a lower resolution than camera original negatives. And then if you ever forced, or if the producers ever forced development to get a certain look or to pull out more light effects or so on, if they ever forced processing in any way, which increases grain, the increase in grain also reduces the resolution that can be recorded on the film. So there are a number of different factors that go into what is the real resolution on film. To give you an idea of what the electronic resolution versus the physical resolution is on film, and these are rough. These are rough estimates, and they're not the same for every type of film. It really depends on the emulsion and how it was shot and a number of different factors. But roughly, for 35 millimeter film, there's been demonstrated up to 16,000 lines of resolution for the best 35 millimeter camera negative. However, if you actually go to the motion picture theater, like the AMC theaters around here, and you watch a motion picture film, you might actually say, that's really not as good as some of the material on my HD TV set at home. Well, there's a reason for that, because the high-speed reproduced 35 millimeter distribution prints for theatrical distribution actually only record about 800 to 1,000 lines of resolution. So if you go into a theater one day and you watch, Harry Potter on 35 millimeter, and then you come back tomorrow and you watch it in the digital theater in 4K, you're going to notice a very big difference between the film version and the 4K version, or even the film version and the 2K version. And that's because of how the film was copied. In the case of 16 millimeter, it's roughly 4,000 lines of resolution as a maximum. Things like news film are probably less because, again, they were quickly produced on cheap cameras. They were force processed in many cases because they basically came back to the TV station and they were processed within 15 to 20 minutes, so there was a lot of force processing to get it on the air, and that lowered the resolution on many types of news film. but 16 millimeter as a whole is capable of about 4,000 lines. 16 or Super 16 is capable of roughly 6,000 lines, again, depending on how it's produced. And then 8 millimeter and Super 8 at its maximum would be somewhere between 2,000 and 3,000 lines of resolution, again, depending on the quality of the stock, how it was produced, how it was developed, and so on. When you convert from analog film to digital, what do you need for preservation? In the case of lines of resolution, you need to get as close to the resolution of the film as possible. Now, again, this is one of those moments where you have to decide, do I preserve on a large scale if I've got a, any collection of any size, or do I do the whole thing and I have enough money to do the whole thing but not do it at a high enough quality? That's one of those decision-making factors you have to go into. Again, if you want to do the best, I can only recommend get as close to the original film resolution as possible. That said, there are very few film scanners that can get anywhere close to 16,000 lines of resolution for 35 millimeter film. I can tell you right now, we don't have one at the library because they are very, very expensive, and unfortunately, we don't have infinite funds. However, if you're doing something like Access, HD or SD will probably do, since it uses common production tools that are off the shelf and are fairly inexpensive. If you are producing for online, you can actually use lower resolution. You can use highly compressed MPEG-4, you can lower the horizontal and the vertical resolution, you can do a number of different things to allow it to be a very small file. However, the one thing I would like to say is if you think that file is going to be around for any period of time, one of the things I just want you to stick in the back of your head and think about is this file going to be around? And if so, will it survive the 2 to 5 years that it will take for a lot more broadband to be available out there? And so when people are starting to download YouTube videos at 4K, and YouTube does have a 4K page now, it's quite possible that you may have to go back and redo your Access files for streaming onto the internet at some point, because people will start complaining and saying, this looks like crap. And they're right, it probably does. I mean, how many of us think that YouTube is actually good quality video? One of the advertisements that I always got a kick out of, I haven't seen the ad in the last year or so, but for about 5 years it ran, and it was a DirecTV ad where there was the DirecTV man with the DirecTV logo on the back of his jumpsuit on the top of a ladder doing the dish to install it, and the homeowner, hairy homeowner, comes up and says, is this good quality television? And the guy looks at him like, you silly homeowner, you. This is digital quality television. And I always, that was always one of my moments, because I always thought, well, internet streaming is digital quality video. It's just really bad digital quality video. And so just because it's digital doesn't mean that it's good. You have to be an informed consumer on that point. Returning to the concept of bit depth, in other words, 8-bit, 10-bit, so on, how many bits are you using to represent each color channel? It determines the number of color shades that can be represented. Anything under 10 bits will show visible contouring in the images that you capture. And current scanners can actually manage up to 16 bits per channel. Now, needless to say, you're going to pay some fairly serious money for something like that. But, what is your end product? How many generations of processing do you have to go through? This is one of those planning factors where is 10-bit capture good enough? Is 8-bit capture good enough? This is where you got to make that decision for yourself. And then, of course, what type of color space are you operating in? I'm not going to make a recommendation other than to say if you operate in RGB, you'll probably almost never go wrong. However, be aware that the standards organizations are actually working on some new definitions of color space, which will actually allow more color resolution and different types of color resolution for production purposes to be captured. And so RGB, which has been the king of the hill for the last 60 years, may be supplanted at some point in the future. So be aware that that may be an issue. Also, when you're actually converting to digital imaging, do you mask or do you not mask? Do you scan to the edge of the frame? Because frames can have very rough looking edges. Or do you mask it in some way? And keep in mind, film tends to weave, and so your masking can also cover up that weaving. Or do you crop while scanning? or do you crop in post-production? At the library, we do any of a number of different things depending on the material that we're dealing with. Now, many old films and things like fast copied or high-speed copied films have a lot of what we call gate weave, where the image visibly moves from left to right or even up and down and left to right on the film. And so what we do is we capture the whole frame plus a little bit at the edges, and then in post-production we rejigger those so that the frames match. And so we set certain points in the image for our computers to pay attention to, and then they bring the registration back in where you don't get a lot of weave to the picture. And that way, especially on old films where the stuff literally goes like this sometimes, it keeps you from getting motion sickness when you watch the material. But that's actually one of the creative things you need to take a look at as well. Do you want to do post-processing like that? Many times these decisions are dictated by how expensive a scanner you can afford, either because you're purchasing a scanner or because you are going out to a post-production facility to do your capture for you. And so there are many different planning factors when coming up with what do you need, what do you want, what can you afford. That's some of the key decision factors. So what's this digital cinema? How many of you have heard of digital cinema? Yeah, not as many as I thought. Well, if you go to any of the major theater chains around here, you will notice digital presentation in their advertisements, and that usually means they're using a digital projector and it has not touched a frame of film. Sometimes from the point of acquisition, it has never touched a frame of film. Most motion pictures today, or at least a majority of motion pictures today, are not shot on film. They're shot on high-resolution electronic imaging cameras. Things like the Red One and the Cine Alta and things like that. So in many cases, film has never entered the motion picture part of the industry. Digital cinema as a term was standardized by a group called the Digital Cinema Initiative. And this is the website if you want to take a look at who they are. They're the major studios and, more importantly, the major theatrical owners as well. In other words, folks like AMC and Regal, United Artists, folks like that, where they decided, especially the motion picture producers decided, we're really tired of spending $8,000 to $10,000 per print to distribute our 2,000 prints around the country for general release. That's a lot of money just in motion picture film to get our film out there. Is there a way to get around that? And so they created digital cinema. And it was accepted by the standards organization, the Society of Motion Picture and Television Engineers. There are two standardized distribution formats, two flavors. One is known as 2K, which is 2048 pixels by 1080 lines. And if you look at it for a second, you say that's an awfully close numbers to HD, which is 1920 pixels by 1080 lines. And eureka, you got it. It's basically widescreen HD that can operate at either P24 or P30 frames per second. There's also a production format or a capture format as well, known as 2048 by 1556. And that might actually be a valid capture format for things like 35 millimeter or 16 millimeter. For 16 millimeter, it might actually be a good preservation format as well. So there are some scanners that you could use for preservation that could accommodate these standards. And then the second one is 4K, which is 4096 pixels by 2160 lines, which is 4 times the resolution of 2K. And if you go to places like AMC at Tyson's Corner or many of the Regal theaters, and in fact, if you ever go to MovieCo, most of the MovieCo theaters are now 4K, and about half of the AMC and the Regal cinemas are now 4K. And it really is a fantastic picture. But keep in mind, these are distribution formats, not necessarily production formats. And so in the case of 4K, there's also a scanning format, which is 4096 by 3112. And so again, this may be a good preservation capture format for 16 millimeter film. And many film scanners today are shipping with this and the 2K format capability. The key thing to keep in mind is both of these formats are distribution formats. When you take a look at an electronic cinema presentation, they are compressed and they have been encrypted for transmission. And so from an archiving perspective, for those of us who are the Copyright Office of the United States, we have to take that into account. And if you ever receive a digital cinema package that has been keyed and encrypted for whatever reason, because it's part of a collection or whatever, keep in mind that's actually one of the technical challenges, isn't necessarily just keeping that digital file extant, but also being able to replay that digital file. That could be a challenge. So the encrypted and the compressed versions are not necessarily ideal for long-term archiving. One of the key things, though, is that these are produced and distributed as files. And there are three key files to keep in mind when you think of digital cinema. There's the digital source master, which is the final edition of the electronic cinema production, the final edited version. There's the final step before compression and encryption, which is known as the DCDM, the Digital Cinema Distribution Master. And this is the motion picture in its final form, but at the highest quality. And the difference between the DSM and the DCDM is things like the DSM is one contiguous file, whereas the DCDM is cut into 20 or 40-minute increments based on the length of 35-millimeter film reels. Yeah, go figure. It's kind of like NTSC. We're never going to get rid of 2997, and we're never going to get rid of 20-minute, 35-millimeter reel timings either. Go figure. And then the final output is known as the digital cinema package. That is the compressed, encrypted, and keyed to the individual projector's serial number. That is the file that actually goes out to theaters. Now, obviously, given that this is an extremely high-quality file, the folks who produce and own this content and don't want massive amounts of high-quality content copied over in China, they have a reason for doing this, and it's a perfectly valid reason. But for those of us who need to archive these things, we need to keep in mind what the challenges are, the technical challenges are, if we ever end up with any of these files in our systems. But what do we call it if we aren't actually producing DCI standard files? Well, at the library, we've migrated to using the term electronic cinema, just like electronic imaging. And so that calls attention to the fact that this may not be a DCI compliant file, and it allows us a lot more flexibility to say this is an electronic cinema file, and it may have different bit depths, color spaces, resolutions than the DCI spec standards. And so for our purposes, we tend to use the term electronic cinema. That is not an industry adopted term. That is our normalized nomenclature in day-to-day work. So if you want to call it something else, feel free. When you take a look at inspecting your film, a couple of quick points. First of all, could it be nitrate? Does it smell like mothballs? Or does it smell, and I'm serious here, does it smell like a wet dog? If it smells like a wet dog, please call us, because that means it's starting to decay. Most 35-millimeter film produced before 1951 was nitrate. And for those of us who know what it looks like, we can actually, by looking on the screen, we can tell the difference between a nitrate print and an acetate print. Acetate is safety film, of course. And that's because they have a different color temperature. Nitrate tends to be a lot whiter, if you will. It doesn't impress a color into the white light coming out of the bulb in the projector, whereas acetate and polyester both have slightly different color temperatures. In the case of acetate, does it smell like vinegar? That means your acetate film is starting to decay. In the case of polyester, polyester for the most part is a very stable format. One of the things you need to be worried about, though, is it scratched? Because polyester tends to take scratches a lot more noticeably than the other two types of bases. In the case of film soundtracks, are they optical or are they magnetic? In the case of optical, are they variable density or are they variable area? Given the time we have today, I'm not going to go into depth, but it's fairly easy to figure out which are which. And if you're not sure, go to Wiki Wikipedia, they're pretty good. Also consult, more importantly, consult your film books because they're actually a lot better. If it's magnetic, treat with caution. The magnetic strips can delaminate easily, and in fact, if you're going to clean film, and if you're going to transfer film, and even if you're going to store film for long periods of time, it usually should be cleaned. One of the problems with film cleaning, though, is some film cleaners, some solvents, treat magnetic strips as if they're dirt, and so the strips will come off. There was one time when I was at Channel 9 and we were running some of the old film, the old news film, and preparing it to be copied before we were going to do a move and send the film off to storage. And one of the folks on a piece of film from the Watergate era stuck it into the film cleaner and used the wrong type of solvent. They used the non-magnetic strip solvent. They used the stuff used for things that don't have magnetic strips. And we looked in the cleaner and there was this little curlicue coming out of the film, and that's because the magnetic strip had been cleaned off the film. So be aware, you need to keep an eye on things like that. The key thing, though, about cleaning is it's not necessarily cheap, but in the end, it makes a better product. If you can afford to clean your film, absolutely clean your film. Any questions? Okay. Let's take a look at moving image digitization and some of the basic concepts. So what is digital video? What does digitization mean? Well, fundamentally, it means it's a system where the visual information is carried using digital numbers instead of an analog voltage. It's a sample of each television line represented as a series of numbers that are defined to mean a certain point on an analog voltage wave, and then the sync and blanking pulses that are within the signal are dropped and are replaced by timing bits inside of the bit stream. Some of the important concepts that I need you to think about are bit depth, and we've already talked a little bit about that, color space, what is the native resolution of an electronic image, what is the native frame rate, a few notes about time code, how do you keep your how do you keep your audio in time with your video, and then a note about the Nyquist limit. In the case of bit depth, again, this is the number of steps from dark to light. If it's black and white, it's from black to white. In the case of colors, it's from the darkest version of that color to the lightest version of that color. It's expressed in bits per channel. So if you mean 10 bits, you actually mean 10 bits per channel. 10 bits from the red, 10 bits for the R, for the green, 10 bits for the blue, which is B, RGB. That means that for every sample, you've got 30 bits of information. In audio, it determines, the bit depth determines the signal to noise ratio of your audio. Now, keep in mind also, what is your color space? Is it RGB? Is it YPBPR? This can affect any processing or post-production of the product as well. One of the reasons I mention this is if you don't have enough bit depth in your captured image and you have to post-process, you have to lighten, darken, de-scratch, take dirt out of it, do various types of processing. That actually requires greater bit depth than if you just scanned it and put the original scan away. And the reason for that is the software requires a greater range of values than the human eye requires to actually see. And if you don't have that greater range of values, you start getting visible artifacts in the processed video. Now, what does native resolution mean? What is the actual resolution of your material? Any conversions from native resolution will be visible in your end product, and some more than others. So again, I go back to some folks consider doing a PAL to NTSC conversion. There will always be a noticeable difference between an original PAL tape, which is 625 lines, and an NTSC version of it, which is 525 lines. Or even if we're talking digital, because NTSC and PAL have no meaning in the digital domain. Is it a 625 line video but 25 frames per second? Or is it a 525 line video at 30 frames per second, 29.9 frames per second, 97 frames per second? And the problem is when you convert from one to the other, it is always visible. Now, really good converters like Snell and Wilcox phase correlators, which cost $500,000, they can do both frame conversion and resolution conversion, and they do a really good job, but for those of us who know what we're looking at, we can always see it. It's things like if you watch Masterpiece Theater and they do a credit roll, not static credits, but an actual credit roll, you'll notice on the odd occasion they tend to do this. They judder on the way up. That's an indicator of a frame rate conversion. If you take a look at that same credit and it's rolling and it's juddering, but also it appears to have a second line, kind of an echo underneath of it as it goes up, that's the indication of a resolution conversion, because the lines don't match up correctly as things move. So the question then becomes, one of the decision-making factors becomes, do we stay in native resolution, 525 or 65, 720 or 1080, or do we convert it to something else? Again, it may be a cost issue, but keep in mind, if you do a conversion, it's never exactly the same as the original. It will always look different. One of the important things to keep in mind also is time code. Most videotapes most videotapes after the mid-1970s, when time code was standardized, come with time code on them. And that time code matches the frame rate of the video that you're dealing with. So if you go through a conversion, you need to make sure that you also do a time code conversion. The reason you need to do time code, or the reason that it needs to be saved, is because that's a very clear definition. If you ever go back into a production environment, or if you ever go into anything that needs any kind of production that needs a time code, that is a unique number for every single frame in that piece of video. And that's why SMPTE time code was created. So if you do a conversion, you need to make sure that you convert. There's also a concept called drop frame, because in NTSC, what we call NTSC friendly rates, like 5997 and 2994, which if you do mathematics is not a very friendly rate at all. But one of the problems is if you use time code that runs at 30 frames per second, but you have a 29.97 frame per second piece of video, for every hour of video, you will be 2 minutes and roughly 30 seconds off on your time code. Your video may indeed be 58 minutes and 30 seconds, but your time code will say that you're 1 hour long. And that's because there's an extra frame every, couple of minutes. And so they do what's called drop frame time code. Every so often, they drop one of the numbers. And that doesn't mean they've dropped one of the frames. They've just dropped one of the numbers. So the time code stays in sync with the video itself. That's one of the challenges when you are converting drop frame time code into a digital file, is also keeping those in time and making sure that your values are correct. One of the other challenges that we've discovered is that the current timecode definitions, which are known as SMPTE 12M, that's the actual standard number, don't fit with 720p 5994 or 720p 60, or anything that's 5994 or 60 frames per second. And that's because back in 1972, when SMPTE 12M was set, no one in their right mind thought we would be creating video at 60 frames per second. And so the maximum number of values that you can have in SMPTE 12M timecode is about 40 frames per second. And so one of the things they've done for time code on 720p 60 is they double the numbers. So for every 2 frames, you have the same number. Now, one of the things the standards organizations are working on is solving that problem, but that has not been solved yet. So be aware, if you ever deal with 60 frame per second or 5994 frame per second video and your time code is looking wonky, that's probably why. One other important concept as well is keeping your audio in time with your video. If you have a native digital videotape, or you have any kind of native digital video, you also have digital audio to go with it as well. If you convert from one line standard to another, you must also retime that digital audio. Something as small, a time difference as small as 2997 versus 30 frames per second will cause audible errors in the digital audio that is timed to the 2997 if you do not retime it for 30 frames per second. That is one of the issues that vexed us when we started doing the digital television conversion for broadcast, was we had these little pops and clicks in the digital audio, and that was a timing error where basically they had taken digital audio and digital video and put them directly into the encoder, and the encoder was doing a conversion of the video, but it wasn't retiming the audio, and so those little pops and clicks were the audio constantly being retimed to get back in sync with the video. Now, one of the things that you may have heard of is the Nyquist limit. And good old Mr. Nyquist, back, I believe, in the 19th century, defined that you needed to sample an analog waveform you wish to represent at least twice as high, or at least twice as fast as the highest frequency you wish to represent in that signal. If you didn't do that, you would get what's known as aliases, which are unintended artifacts which were not in the original audio or video. You can always sample higher than the highest frequency without penalty. You can never sample a lower rate without penalty. And by penalty, I mean artifacts, whether they be audible artifacts or visual artifacts. In video, for example, NTSC video has a 6 megahertz picture bandwidth. That means that you need a minimum of 12 megahertz worth of sampling. And in fact, the SMPTE standard for SD video is 13.5 megahertz for SD and 74.25 megahertz for HD. In the case of audio, the theoretical limit for human hearing is 20 hertz to 20 kilohertz, and so your highest frequency is 20 kilohertz. And so you need at least 40 kilohertz sampling rate for digital audio. That's why, or one of the reasons why, for CDs, commercial CDs, the sampling rate is 44.1. And in fact, in preservation, we do up to 192 kilohertz. At the library, we tend to do 96 kilohertz for our sampling. Now, here's a trivia question for you, and it may or may not relate to any audio preservation work that you may do, but I have this trivia question for you. Why 44.1? Why do CDs have a sampling rate of 44.1? Why not 44? Why not 45? Why not 48? Oh, wait a minute. Yeah, we have a 48. But anyway, why do CDs sample at 44.1? Anybody want to take a stab at that? Wow, nobody. Usually someone takes on my challenge. Well, the reason for that is the original recorders for digital audio, the only thing that could develop enough bandwidth to record digital audio was 3/4 inch videotape recorders. And so if you come down to us in Culpeper, we have a whole row of gray colored Sony 3/4 inch U-matic machines, which are digital audio recording and playback devices. And the reason 44.1 was developed as a sampling standard is because it's a submultiple of the color subcarrier recorded onto the videotape, which is 3.5758945. Yeah, go look it up. Go for it. So that's why 44.1 was developed. It's a mathematical relationship to one of the subcarriers that's actually on the videotape. And that allowed digital audio to be recorded on color videotape. Now, when you're doing an analog to digital conversion, there's 3 basic steps. Once you've come up with all your decision making, you're at the point where you're actually ready to start doing the conversion, there are 3 basic steps: sampling, quantizing, and coding. In the case of sampling, it is where the analog video waveform amplitude, that means the strength of the video. Remember, we have video that goes like this, from dark at low voltage to white or light color at high voltage. You need to be able to sample that at regular intervals and then convert it to a set of digital values. The number of samples per second is known as the sampling frequency. The analog sample or analog signal must be sampled at a minimum of twice the highest frequency within the signal, and this is known as the Nyquist limit. Now, you may say to yourself, well, how do you know what the highest frequency in a signal is? How do you know for sure? And the folks who have done analog to digital converters have actually put what they call low-pass filters onto their converters, where anything above 20 kilohertz for audio or above whatever the highest frequency for video should be, it will actually cut those frequencies out. So you do not violate the Nyquist limit, because if you did, you would see visible artifacting in the audio or in the video and hear visible artifacting in the video or audio. In the case of Video, again, you need at least 2 samples for every single wave. If you don't, or for every single cycle in the wave. If you don't have that, you cannot accurately represent that wave. Step 2 is quantizing, where for each sample taken from the continuous waveform, decisions are made as to what digital value will be assigned for that given voltage. If the voltage value falls between the 2 numbers available to represent the 2 closest values, a decision must be made as to whether the higher or lower value will represent that particular value. Functionally, it's the same as rounding up or down. And so you'll notice, if you take a look at this waveform, there are some samples that are slightly above, there are some samples that are slightly below. You have to make a decision about how close that gets between the 2 digital values that you can set. And then make a decision about which value you're going to represent. Now, I've had folks in the past say, well, that means you're injecting a quantizing error into the signal, whether it be audio or video. And the fact is, even with audio, which is a very low sampling rate, the quantizing error is actually very, very small as a percentage of the frequencies that are represented within the original analog signal. So if you take a look at the original analog signal and then a signal regenerated from a digital to analog conversion after you've converted to digital, they are most of the time virtually indistinguishable from each other. You cannot see the difference even on lab quality equipment. So the difference for the most part is very, very slight between analog and digitized audio. Step 3, well, one of the key things is as long as you've met your technical parameters, you've met the Nyquist limit, you've got sufficient bit depth, your sampling frequency is high enough, as long as your planning factors are in place. Step 3 is coding, where we actually assign standardized digital numerical values to the sampled waveform. For 8-bit video, black or darkest in SDI is assigned the digital number 16. You'll notice that's not 1 or 0, it's 16. And the reason for that is the values from 0 to 15 are housekeeping or synchronization bits. And so you have to include a little bit to keep synchronization, keep the signal synchronized. And the highest value, or the lightest value in the case of color, in 8-bit video is 235. All other shades of black and white or light to dark must fit between 16 and 235. Now here's one of the key points, the differences, one of the important differences between 8-bit and 10-bit video. 10-bit adds 4 times more values. So instead of 16 to 235, you have 32 to 1024. So you've got 4 times the resolution, or 4 times the number of steps. You can get a much more fine gradation between light and dark within your video signal. So that's the difference in those 2 little bits. It's the difference between 235 values versus 1024. Now, electronic cinema cameras and film scanners are capable of up to 16 bits per channel. And I guess this got cut off. Each of the 3 color subchannels that are sampled, in other words, RGB or YPBPR or XYZ. So I apologize, that got cut off. Oops, we seem to have repeats in here. Sorry about that. So here's an example. So for 10-bit video times 3, you have 30 bits per sample. And for 16-bit, you have 48 bits per sample. Some of the related steps are you need to decode any composite video. Remember, composite video is defined as where both the black and white, or the luma portion of the signal, and the color portion of the signal are all in one signal. They are all contained in a single signal. You need to decode that composite video to its luminance and color difference components before you sample it. Of course, this is not needed if the signal is already in component form. You need to bandwidth filter your luminance and your color difference signals before you convert to digital, and then, again, this is to keep from violating the Nyquist limit. And arrangements must be made for sampling of the color signals. In other words, if you decode NTSC, that's decoded into Y, I, and Q. I and Q are defined as certain values of YPBPR. You need to get them back into the YPBPR values, or the RGB values if you're converting to RGB. So let's go back again and think about the proper terminology when we say component. What does component really mean? The only true component at this point is RGB. Now there's a flavor of RGB, or there's a variant that is used for digital cinema called XYZ. That's also a valid component signal. However, most of the work that you're ever going to do is going to be centered around values of RGB. So I'm going to concentrate on those. The component color difference signals are what I mentioned before, YPBPR, which also means Y, R minus Y, B minus Y. And what that means is if you take RG and B, if you take a look at the green channel, the G in RGB, that actually contains a little bit of R and a little bit of B. So depending on how you do your mathematics, you can make G equal Y. So Y is your luminance signal, in other words, your black and white portion of your picture. And then you can subtract the elements of red that are part of Y, R minus Y, and the blue parts of Y, B minus Y, and you need only transmit the signals that aren't in G, that aren't in Y, and that's why it's called Y, R minus Y, B minus Y. And so what that means is you can represent very closely what the original RGB values are, but the R minus Y and the B minus Y signals can actually be half the frequencies that are in R and B in RGB. Does everybody get that concept? So the reason also for doing this is later on, when they came up with the sampling standards, they also digitized the two color difference signals at only half the data rate of the Y signal, because the human eye is not as sensitive to color. So it was also a form of bit rate reduction. Now, when we talk about YPBPR, that is an analog way of describing component color difference signals. In the digital domain, it's known as YCBCR. So if you ever see an analog device, and I have seen these, that say YCBCR on them, that is a misnomer. That is not a correct way of using the term. Now, as I mentioned earlier, the two types of composite are YUV, which was used in PAL analog composite and tends to still be misused to signify component color difference in many contexts. And then there's YINQ, which is used in analog NTSC composite. Color difference channels may be subsampled. It's an easy way to reduce your bit rate before you apply actual compression in compression systems. One of the key points that I need to make is if you're considering using MPEG as your compression standard, MPEG is a YPBPR-based compression standard, not an RGB-based compression standard. So it subsamples the color component of the signal, and I'll show you that in a second. However, one of the reasons they do this is it exploits the human visual system's reduced ability to see color detail. It's the digital equivalent of the chrominance bandwidth reduction that happens when you encode into NTSC and PAL, because you have to go from RGB into YIQ to get from RGB to NTSC. So if you've ever seen the term 444, this is what it actually means. There are 4 samples of Y and the 2 color difference samples. For each sample, or for each value, you have 4 samples of a given waveform in a given period of time. Now, because the human eye doesn't see color terribly well, one of the ways you can actually reduce the bit rate of the signals that you're capturing is you can sample at 422. You're still sampling the portion of the signal that the human eye sees the best, which is the black and white, or the luma portion of the signal, but you only sample half as many of the 2 color difference signals. And again, that's a way of doing easy bit rate reduction without having a great deal of impact on what the eye finally sees. Now, the negative to that is production equipment that requires a lot of color processing really needs to see 444, because that's mathematics. You know, computers don't care what the resolution of your eye is. They care how much actual chroma resolution you have. So many production houses standardized on 444, not 442. And since we're going a little long, I'm going to skip over this. One of the key things, though, to keep in mind is there are other forms of chroma subsampling. In the case of DVC Pro, if you've ever heard of the format DVC Pro, it uses what's known as 411 sampling, which means, again, it still samples for every sampling point, 4 samples of the luminance, but it only does 1 sample of the 2 color difference channels, which means you're now getting only 25% of the original color. Now, there's an interesting and not terribly well expressed way of expressing a form of color encoding in MPEG known as 420. 420 does not mean, in this case, it's a nomenclature change. It does not mean 4 samples of Y, 2 samples of CR, and no samples of CB. They've done a misnomer here. What it means is that for every sampling point, MPEG-2, if you use main profile, main level, or high profile, main level in MPEG-2, and if you don't know what those are, look them up or drop me an email. I can explain that to you. What MPEG-2 though does, and this includes all production that includes 420, anything that's encoded at 420, what it does is it takes adjacent pixels on adjacent lines, like line 1 pixel 1 and line 2 pixel 1, and it averages the chroma samples between the 2 of them. That basically means you're going from, in the case of DVC Pro, where you're only recording 25% of the original color to begin with, you've now averaged 2 samples together, so you're now at 12.5% of the original color that was in the original signal. Now, if you think about it for a second, if you have an interlace signal, which most of our NTSC era video was, and you do a quick pan, there's a time difference between the first fields, which are all odd line, and the even fields, which are the second field, which is all even lines, where you can actually have a serrated edge on the video because the 2 are difference. It's the difference in time. So what happens if you average line 1 pixel 1 and line 2 pixel 1 together at that moment? You get a color value which doesn't look anything like the color value of the original line 1 pixel 1 and line 2 pixel 1. So that's why in many cases, if you look at MPEG-2 video, you get weird color fringing in certain areas, and that's a known artifact of MPEG-2 encoding at 420 chroma with interlaced signals. So if someone says to me, we're thinking of using MPEG for preservation, my first response is, bleh. My second response is, let's walk through the ramifications of this, because once you throw away this information, you will never get it back. It's like going from from digital to analog NTSC and back again. Once you throw away the information, once you put the artifacts in the signal, you can never clean up the mess again. That's also why I discourage folks from using DVC Pro, the original DVC Pro, not DVC Pro 50, not DVC Pro HD, the original DVC Pro, which is still very common in this business. I discourage them from using that as a archiving format, a production format, a distribution format, if they're ever going to have a library of material that needs to last for a long period of time. Because especially if you go from DV into MPEG, there are direct first generation problems with that, and this is why. Any questions on that? I know this sometimes is a difficult concept to get a hold on. Yeah.
Does it matter what your original format is? Is that true across the board? I mean, most of our material is 3/4 VHS.
You mean if you copy from 3/4 in VHS to DV?
Yeah.
Versus going to MPEG versus going to something else?
Yeah. Are the benefits the same for going to JPEG 2000 from a low-res format?
Not at all. Not at all. One of the key standard points within JPEG 2000 is it not only needed to be able to accommodate all of the original color spaces and all of the bit depths, but that it doesn't do chroma subsampling like this. And so unlike MPEG, which by its nature, MPEG was designed as a transmission format, whether it was transmission to computers or it's transmission via satellite or over the air. That was the whole purpose of MPEG. It was not meant for production. It's just, it was really cheap, so it made its way into the production sphere. And so if you have the choice of going from your original analog to something that is not DVC Pro, the original DVC Pro, or not MPEG, I would encourage that, because what little color information is already in that analog signal will get decimated even further just by the fact of how the two formats are coded. And Lord help you if you then go from a DVC Pro into an MPEG as a file format, because then you have not only the low color resolution of your original analog, plus the 411 sampling of DVC Pro, plus the problem with 420 with MPEG. So you've got 3 different problems all going on at the same time. So if you want to get as close to the original analog, and let's admit, let's be honest here, original analog is not that great. If you take a look at digital 525 versus a VHS or even a good 3/4 inch, there's no comparison. But that also means that if you're going to keep the original material as good as you can get it, you need to not make compromises with that original analog material. I remember one of the first moments I realized what the real difference between digital and analog was I was the engineer for the Fox News Washington Bureau over here on Capitol Hill in 1996. And when we first turned on master control for the very first time, it was a completely digital facility. We had our outbound digital monitor, and then we had our analog satellite return, which was NTSC. And the difference, exactly the same monitors, Sony broadcast monitors. And there was a visible difference between the outgoing digital and the return on analog. And the only difference was the NTSC encoding. You could see dot crawl, you could see the difference in colors, you could see a whole bunch of different things, the difference in resolution. Like, I bet you didn't know this, but NTSC and PAL cannot do purple. They cannot do genuine purple. It's always either bluish purple or reddish purple. You can't get to lavender. You can't actually get to lavender. And so that's another reason why you don't want to take a digital signal and encode it analog and then go back to digital again, because you greatly lower the amount of color space you can operate in. Any other questions? Okay. Let's see what our time is. Okay, we're running a little short on time, so let me get through the rest of this. Component video signals are familiar and yet different. If you actually want to see what they look like, this is what they look like to those of us who actually do this for a living. The color bars that you see here are the color bars that I took a photograph of when I was at PBS 10 years ago in master control. We had both an SD and an HD master control. So these are the color bars that stations were seeing, and this was 6:20 at night, so clearly I was working late that night. And then here are the waveforms and what they look like. If you take a look at analog waveforms, there are 2 different versions. There's the waveform monitor and the vector scope, and that's the rest of the top line. And then if you want to see what they look like as your component color difference signals, that's what they look like at the bottom. And I'm going to skip this, but if you take a look at high definition video, again, we have color bars taken within minutes of the SD color bars. And then, since there is no such thing as composite in HD, the 2 other pictures at the top are, first of all, if we actually overlaid the 3 signals together, this is what they look like in the middle there. And then side by side in what is known as a parade. So if you ever see a button on your scope that says parade, that's what that means. And then if you actually take a look at the individual color channels, you've got Y, CR, and CB across the bottom. Now, in our case, we were given the mission to digitize everything. And for us, that means consume mass quantities. Yes, if you actually come and visit us in Culpeper, you will notice that there are Coneheads posters in certain rooms, and those are the consume mass quantities rooms. So luckily we have a sense of humor about what we do. And so since our archive is supposedly going to be maintained for the life of the Republic plus 4,000 years, we tend to have a different perspective on the word longevity. For our purposes, our archive, the files should be able to stand alone without references to external databases, which means we have to wrap lots of metadata in our files. We digitize the items in their original quality, In other words, we choose a high enough sampling rate for both the audio and the video. We also keep it in the original resolution. If it's 525, if it's NTSC, we convert it to 525 digital. If it's PAL or CCAM, we convert it to 625 digital. And obviously, if it's 720 video, we leave it at 720. If it's 1080 video, we leave it at 1080 video. And then for film scanning, we're studying a couple of different things. We're not quite there on preservation film scanning yet. We're starting to do our first tests for 4K for 16 millimeter. We're actually going to do some of that compare and contrast between 2K by 1556 and 4K square. And then we think 8K for 35 millimeter may be good enough for preservation. Again, that's something we're going to be testing as affordable film scanners come into become available. We use as much off-the-shelf products as feasible. The only things we invent or the only code that we write are things that we cannot get from commercially available items. If on the odd occasion we need to take something that almost fits what we need and ask the vendor to adapt it a little bit to what we do, that's actually a lot less expensive than reinventing the wheel. So we tend to not try and reinvent the wheel. The positive of that also is if we can solve some of the problems with using off-the-shelf technology, that means that folks like you can solve those problems with off-the-shelf technology as well. So we use industry standards as much as possible, and we create realistic long-term goals and budgets based on, you know, what we can actually manage. For audio, for moving image content, for video, we tend to do 48 kilohertz 24-bit. For film, we're looking at 96 kilohertz 24-bit, because keep in mind we're using original production quality masters, whether it be the cut negatives or it be a release print. We're using high quality masters. And then we're also planning for the multi-channel mixes that we get from copyright. In other words, we may get a 6-channel distribution master in English, in French, in Vietnamese, in 3 versions of Chinese, in half a dozen different languages. And so we have to also accommodate not only that 6-channel English, but all the other 6-channel mixes that may come along with it. Now, as I mentioned, video, we compress using JPEG 2000 lossless, and in the standard, that actually means reversible 5:3. It is mathematically lossless. And we've actually done a lot of testing to see whether or not our encoders are really mathematically lossless, because JPEG 2000 does have a setting that allows you to do visually lossless, which means, again, it's very high quality. The human eye shouldn't be able to see it, but you're actually throwing away some original content. And so we're working on test signals that we have a fairly high confidence with at this point that will show us any kind of impacts of compression on the screen. And so far we've been very pleased with our JPEG 2000 lossless encoders. The file format that we've chosen is a standardized file format known as MXF, and the flavor of MXF that we use is OP1A. If you want to know what that means, I would suggest you go and read the SMPTE standards. Basically, MXF was created to be a file-based workflow for a whole range of different production workflows, including editing and archiving and a number of other functions. And so there are flavors for each of those types of functions. And so for film also, what we're working on developing is, again, JPEG 2000 lossless, MXF OP1A wrapper, that's our goal. However, in the meantime, for the material, until those encoders are actually available, and the first one I think we're going to be testing sometime in the next year or so, but until that actually happens, any material that we need to save today, we are using the DPX file standard, which is uncompressed, with BWF audio, which we believe is, should be 9624 for the broadcast wave format. And for us, that is a short-term, we believe, is going to be a short-term expediency. In other words, until we can get to JPEG 2000. But time and experience will tell. We may never get there. A few notes about Born Digital. There are 2 basic types. Now keep in mind, once you're in Born Digital, you're talking about, for the most part, everything that we've already talked about when it comes to formats and line standards and frame rates and all of that stuff. All of that applies to what's inside the Born Digital content. So here I'm just talking about the types of Born Digital content. When it comes to physical media, it could be videotape, in other words, a digital videotape. It could be optical discs. which is not necessarily files, but can be turned into files. Then there are things created as files themselves. In other words, XDCAM, AVCHD, some forms of MPEG-2 that are file-based. And then there are hybrids, in other words, files that are saved on solid-state media. Technically, that's both physical media and a file at the same time. Same with hard drives, same with optical discs that save as files. They're hybrids. The easy part of moving image content that's born digital is the program material is already in one of the picture and audio formats we've discussed. So all rules of what's best hopefully have applied up until this point, but whatever we've got to deal with. If it's 420 compressed MPEG-2, we've got to deal with 420 compressed MPEG-2. One of the more difficult things, though, is it can be in any of a dozen different flavors of compression. And so, and just as with tape formats, over time it will become difficult and in some cases probably impossible to play back certain formats or flavors of common compression formats. And I say that because one of the things that we've run into, both in the production industry and also in our archiving function as well, is that MPEG-2 is not a standard per se. It is a standardized set of toolkits. And the difference is this: a standard, like 3/4 inch videotape or 1 inch videotape or D2 videotape, that is a hard, fast standard. If you don't get all the parameters correct, your material will not play back. MPEG-2 is a set of toolkits, which basically means anything within that toolkit, as in the bit rate or the color space or how you read certain parts of the raster or how you develop certain values, all of those can be done differently. So MPEG-2, main profile, main level, could mean any of 100 different flavors of MPEG-2, main profile, main level, because it all depends on how the software writers wrote the software to do their encode. And so the reality is, you may have MPEG-2. You may have an MPEG-2 player that can do main profile, main level. That doesn't mean you will be able to play back video that was generated by a Scientific Atlanta encoder from 1999 that you have a file from, because they did their flavor of MPEG-2, main profile, main level. And one of the problems that we ran into when I was at Intelsat was we actually had a problem with Scientific Atlanta encoders did not work well with certain types of MPEG-2 decoders, Tamberg, Tiernan, whatever. And so keep in mind, if you have born digital content that's in any of the MPEG standards, you may or may not be able to recover that content into the future. And so from our perspective, we keep the original file for the record, especially if it's a copyright submission, because we're legally required to do that. However, we convert the essence and the key metadata to JPEG 2000 lossless MXFOP1A at the native format, at the native frame rate, because that will allow us to maintain access to the material in a meaningful way when we no longer have the software that can effectively recover the original MPEG-2 content, because that's going to happen one of these days. So keep that in mind. So why did we choose JPEG 2000 lossless? Well, it was the first practical compression standard that didn't throw away any of the picture content. When we say losslessly compressed, we mean when you decompress it back to uncompressed, you cannot find any missing data at all. So just to walk you through some of the numbers, uncompressed standard definition operates at 270 megabits per second. Uncompressed HD, up to 1080 lines, operates at 1.485 gigabits per second. And if you do the math, that means a file size of 121.5 gigabytes per hour for SD and 668.25 gigabytes per hour for HD. So this is your storage requirement for 1 hour of video, SD or HD. Now, you start taking a look at millions of hours, and you go, I really don't want to go to Congress with that number. Doesn't mean they wouldn't give it to us, but you never know. So my basic response is, ouch, that's a lot of space. So with JPEG 2000 lossless, what this allowed us to do, and again, we're talking about the reversible 5:3 profile, it means we get an average of roughly 2.3 to 1 compression, and that's dependent on program content. If you have all black, it actually compresses at 100 to 1. That's actually kind of cool. We had HD that was all black, and I won't go into why, but that's another story. And our file sizes were, 500 megabytes, not 500 gigabytes. That's because the video was all black, but that's another story. So if you take a, look at the comparison, you take 121.5 gigabytes per hour for SD, divide by an average of 2.1 or 2.3, that gives you roughly 52 gigabytes per hour for JPEG 2000 lossless. With HD, again, divide by an average of 2.3, that's 290 gigabytes per hour. That's still a lot of storage, don't get me wrong. That's a serious amount of storage. But that's 2.3 times less storage that we have to accommodate. Now, one of the key points of this, though, is that we will always need to make sure that we have JPEG 2000 lossless capable decoders into the future. That's one of the key parameters. And so clearly, a lot of our effort is not only creating the content, but also working with vendors and coming up with standardized coding and designs that will make sure that for ad infinitum, we will always be able to decode JPEG 2000 lossless files of whatever type they may be. So uncompressed is available toolkits right now. If you can take the storage that it requires, that's a perfectly valid decision, absolutely valid decision. In our case, we decided that the 2.3 to 1, when we're talking about millions of hours of content, had some real monetary impacts for us, and we made the decision to go ahead and do it. And because we've already spent the money on the migration facility, the slight amount of extra money to make sure that we keep JPEG 2000 players available to us ad infinitum, that's not a large cost based on the rest of the plant that it took to get to the point where we actually develop actually have the files in hand. So for us, it was real money. For you, uncompressed may be perfectly fine. So where do we store all of this material? Well, very quickly, there's a difference between archive and repository, and given that we're running over, I will basically say this. Archive is where you have, the contents are not meant to be accessed except when absolutely necessary. A repository is, stuff where you also keep day-to-day, files that are regular business files. In our repository, we have a 200 terabyte SAN, which is where we put all the files before they get written to tape. We have a tape library, which currently has 9,000 slots installed, and our data center is designed for a robot up to 37,500 slots by maybe 2013, but it really depends on what our increase is over time. Clearly, we're not going to buy machinery until we actually need it. Currently, the format that we're using is what's known as T10000, and it's the T10000B variant. There was an A, now there's a B, there's about to be a C. The T10000B tapes store 1 terabyte per tape, which means we have an installed capacity of 9 petabytes. And the Sun Storage Tech folks have said that we have an upgrade path to 48 terabytes per tape by the year 2019. So hopefully the 37,500 slots that we have in our localized tape library will be fine. We use the SAMFS file system, and as of Friday, we had 1.016 petabytes in the can, and so we passed the petabyte level as of last Tuesday. We're very happy about that. For being in production for under a year, or under 2 years, and having the first year of production being almost all audio, having a petabyte in the can, makes us very, very happy. And we're increasing at approximately 30 to 40 terabytes a week now. And we're not sure when we're going to hit the first exabyte. It depends on a whole bunch of different factors, but we think somewhere between 2013 and 2017. However, what that does mean is that we're in a race with the technology upgrades. When the T10000C tapes come out officially, we're already testing the format now, those will be 2 terabyte tapes instead of 1 terabyte tape. And so at that point, we have to make the decision. Do we migrate everything we've already done, or do we just exhaust our 1 terabyte tapes and start writing to 2 terabyte tapes? And I think from a budget perspective, it makes a lot more sense to write to the 2 terabyte tapes after we've exhausted the 1 terabyte. And then when the 4 terabyte tapes come out, the Ds come out in 2 to 3 years, we will then migrate all of the 1 terabyte tapes. But talk to us in a year or two. We'll see whether or not that's a valid thought. So you'll notice I've used a couple of different odd little terms here, and these actually stand for MIBI, GIBI, TIBI, and so on. And the reason for this is there's a difference between base 10 measurements and base 1024 measurements. And so when you start looking at the petabyte level, the difference between kilobit and or megabit and MIBI bit and so on starts to really make a difference. And so you'll notice in many of our terms we're going to use TIBI, KIBI, MIBI, and so on. That's actually an ISO standard that has been developed to make sure that we document correctly the difference between base 10 and base 1024 when we're talking about storage. So why did we choose T10000? Why not LTO? Because if you look at LTO, you can get 1.6 terabytes per tape, which is actually quite affordable. Well, in our case, bit error rate matters because our data set is essentially permanent. The archive contents must stand on our own, and again, ignore external databases, must be, access to be able to tell what's in the file. Our files must be format agnostic and so on. When you get to the petabyte level, 10 to the negative 17th bit error rate is GB bits worth or gigabytes worth of errors within your petabyte archive. And so T10000K has the best current bit error rate available, which is 10 to the negative 19th errors. Also, the IBM HPSS system, they also achieve 10 to the negative 19th. However, all the other storage systems, the best they can do, and this includes LTO, and no negative things against LTO. It's a low-cost format that does very, very well, but it was designed as a sort of as a consumer format or as a mass-scale format. And so it was not designed for our type of use, which is long-term, and by long-term I mean centuries, preservation of data sets. It was developed for consumers who basically have a 7 to 15 year planning window. And at that rate, 10 to the negative 17th is perfectly fine for as a planning factor for bit error rate. But for us, it's not. And so when you're migrating every 5 to 10 years, your entire library, bit error rate within that library starts to make a real difference, because every bit that's been flipped, we either have to flip it back, figure out a way to flip it back, or we have to document it, and it may be lost information. And keep in mind, most commercial IT equipment has bit error rates at best of 10 to the negative 14th. And so when you think about buying that $300 e-machine at Best Buy to do all of your digitization, just keep in mind that thing probably isn't even getting to 10 to the negative 14th bit error rate. And so you need to take into account what are your bit error rates in the systems that you're working with. And how often also do you check data integrity? You can, just by reading a data tape, you can also damage that data tape. How often do you migrate also? Individual files, we're probably going to migrate every 5 to 10 years. And a lot of folks have also said, well, what if you don't get your metadata correct in this first pass? For all this content right now, are you going to have bad metadata? And our feeling is that we are going to be able to update metadata as we do our migration. So whenever the 1 terabyte tapes go to 4 terabytes, at that point, if we have metadata updates, which could be cataloging updates or whatever, at that point we'll update our metadata. So what about some of the other formats, like optical disc formats? Well, at this point, we don't consider them archival because we're noticing a fairly large percentage of non-recoverable data errors in optical discs at 5 years. And that's actually pretty scary. So what we were talking about earlier, which is, at least in our division, we are migrating as many of our optical discs to ISO images as possible. We're not willing to trust the optical discs for our archival storage at this point in time. But what about spinning disks? What about hard drives? Well, if you take a look at the math, they don't exactly lend themselves to scalability. The exabyte size of a farm of hard drives, even at very high capacity, is going to be physically huge. If you keep them spinning constantly, now keep in mind, there are folks like Google and Yahoo who need to have these huge server farms spinning constantly because they need constant access to their material. And that's perfectly fine. However, there's a reason Google located their major data centers in the far northwest next to the hydroelectric power plants out there in Washington and Oregon. It's because they suck an enormous amount of juice. And even if you use the low power mode, which uses 30 to 60% of the power of fully spinning disks full time, that's still a very serious amount of power. And also, strictly speaking, we don't really consider them archival because every single disk within that array will probably be replaced within 7 years. I don't have to say that about my magnetic tapes. And that's not only a lot of resources because we have to buy replacement disks, we have to have the people to keep replacing them, we have to have systems to monitor, when the drives actually fail, but it also means that you've got a lot of disposal risks. You've got the heavy metals that are in the circuit boards, you've got a whole bunch of other things that come into it, which when you start talking about large quantities of electronics, you have to take into account. But keep in mind, we're a large consumer, and so that's important to us. And finally, what about solid state? Well, at this point, it hasn't been able to scale to large sizes affordably. In other words, the storage costs seem to be 2 to 4 times, the cost of a comparable amount of spinning disk and tape. However, it is worth watching. One of the key sobering facts, though, is that historically solid state memory has not aged well. If you take a look at how individual memory chips age over time, they start losing connections within a couple of years of being manufactured. And that basically means your bit error rate is rising tremendously. Now, one of the ways that we check whether or not bits are flipped are cryptographic hash sums. They are numbers that tell us what the original size of our file was down to the bit. Currently, we use SHA-1 at Culpeper, which is a 160-bit checksum, which can show a bit flip in file sizes up to 2 to the 61st power file size, which is a fairly substantial file size. There are others, though. There's MD5, there's SHA-2, which is 256 bits, there's SHA-3, which is 512, and so on. What that allows us to do, though, is to find out whether or not any of our bits are actually flipping, which could be a tape failure, could be a drive failure, could be a system failure of some sort. So when do you check your repository for errors? Well, this is, again, one of your planning factors. It's cost in personnel, cost in time and machinery, the chance of damaging the tapes by reading them. In our case, we've already checked our entire archive once, and we've had no bit flips in nearly a petabyte of stored material. Now that's, material that's less than 2 years old on fairly new machinery. There's a good chance that's going to change. If you talk to me 2 years from now, that may have changed by then, because the machinery will be older, certainly the people will be older, and the tapes will be older. So, probably every 12 to 24 months, we're going to check all of our content. But again, that has to be matched with how often do we have to write new material into the archive and how often do we have to do a bunch of different functions. So some of our future challenges is, of course, finding enough equipment to keep going. And in fact, since we're already running over, I'm going to keep going with this and let you guys read that. If you ever come down to Culpeper, you're welcome to come down for a visit. We also show movies free to the public Thursday, Friday, and Saturday of most every week. If you want to find out more, go to the website. Please call before you come. Some suggested resources, especially the JPEG 2000 standard. For those of you who are uber geeks, it's actually kind of interesting reading to see how they walked through. And if you read the MPEG standard and the JPEG 2000 standard, you can see the real difference in thinking and technology between 15 years ago and today. Dolby is also a very good resource for digital audio, both compressed and uncompressed. There are several books and white papers that I would recommend if you want to know more. Some of them are very technical, some of them not so much. So whatever your comfort level is, I would recommend it. If you can find a copy of Envision's The Book and The Book 2 on digital audio, they are absolutely first-rate, normal, everyday English descriptions of digital audio. They're fabulous if you can still find them. And here's some other suggested reading as well. These are the folks who over the years, and I've been doing this for coming up almost on 20 years now, who have helped out. And so thanks to them for everything that they've given us. And if you'd like to contact me, feel free to email me at the email below, jsny@loc.gov. Thank you for staying. Any questions?
We have a question from one of the attendees through the webinar. So when all is said and done, is it better to hold on to sticky shed tapes in the hope that a better treatment will be discovered rather than try the baking solution, which may be a one-off?
You want me to repeat that question? So what?
Incorporate it in your answer.
Okay. The question basically was, is it better to wait for possibly better treatments for sticky shed, or do you go ahead and migrate them now by baking? That's one of those trial of Job questions. If your tape is in bad enough shape, migration is more your friend than waiting, given that we don't have anything other than baking that we're sure of right now. If you feel you can wait 2 to 5 years before you migrate in the hope that we may figure out something better, I think that would be a valid decision. If, however, you think that the tape may get significantly worse or unreadable in the next several years, I would say go ahead and bake and migrate that tape. It really is one of those on-the-ground questions where you got to decide for yourself. Is your tape bad enough that you got to get the material off? And there are plenty of tapes out there that are bad enough. Or do you hope for the best in the future? I'm fairly hopeful, but given that I have no hard data on anything other than baking at this point, I cannot make any promises that there's going to be something better. Anything else? Anybody else here? Yeah.
What about 3D?
What about 3D? What would you like to know? Because that's giving me heartburn right now. There are 6 different flavors. What would you like to know?
Because I didn't hear it mentioned, I'm curious.
Oh, I was really hoping someone wouldn't ask me about 3D.
Withdraw my question.
No, I will actually go there a little bit. Is there anything specific that you want to know about it, like archiving, how to archive?
I'm just a general.
Okay. The fact is 3D has gotten to the point where there are affordable production model cameras out there in the $20,000 range, and there are going to be consumer model cameras in the $5,000 range probably by next year. So clearly we are going to have to deal with 3D before we want to deal with 3D. That said, there are at least 6 different flavors of how to do it. There are several D-Cinema specified ways of doing it in the theater. You've seen Disney 3D, you've seen Real 3D. If you look at the brand names in your movie listings, you can see the different ways that they actually present it on the screen. There are half a dozen ways that the content is actually created and transported through file or on tape or whatever. And so how we're going to preserve those in a final archival format, I don't have a good answer. I can make a best guess at this point, but given that the standard has not been set, it's a guess at this point. The SMPTE, which is the standards organization for both moving image and video in general, is working on a standard that allows you to do left eye on top, right eye on the bottom, where you have, instead of 1920 by 1080 or 2048 by 1080, you have a 2048 by 2160 frame. So it's carried as one large top-bottom frame, left on right, top on the bottom. That allows you to archive full quality, and clearly there would need to be a 4K version of that. And if we actually do some of our old 3D films in our collection that aren't anaglyph, where we actually have the separations, we're probably going to have to, do a high-resolution film scan. So you can see why my heartburn is starting to, rise. And then, because it is twice the frame rate, double your file sizes. Yeah.
Tape versus spinning disk, you said that the disk you replace every 7 years, but what's the equivalent life for the tape?
Well, with data tape, the vendors, and caveat emptor, the vendors are saying for high-grade data tape, they believe that they will not have appreciable bit errors out to 30 years. Now, with magnetic tape, given the age of some of our analog tapes, I think if it's manufactured correctly and we don't have problems with sticky shed, which is a problem of how it's manufactured, I think that's possible. However, I would not count on your data tapes having not significant bit error rates more than about 10 years, and that's a rule of thumb, not a hard, fast fact. But given that that's 10 years as opposed to 7 years, and given that that's 10 years of not paying for electric power and people to replace and yada, 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 there are also some other economic reasons to think that there's a good reason to trust data tape. So the key decision-making factor is, first of all, can you afford the upfront cost of data tape? Because, you know, it's $150 a tape, plus the drives, plus the systems behind it. And many people or many institutions can't afford something like that. But there may be third-party vendors who could give that to them. And so at this point, what we're going to do is we're going to study when we do this first migration from B to C, or we do this first move from B to C, and then we go from C to D when we start copying the 1 terabyte tapes to 4 terabytes. We're going to keep some or all of our 1 terabyte tapes for a period of time probably, and study how they age and see whether or not that tape format does indeed age well. Because in the end, the only real way to get good data on tape aging is to study aged tape. So my quick answer is I still have a lot more faith in the longevity of data tape versus spinning disk. However, if someone can come up with the substance that will not delaminate and will last 100 years and allow me a terabyte in a 4x4 inch square, please come talk to me. You're my new best friend. Any other questions? Yeah.
Where can fundamentals of digital video be purchased? Can't find it on Amazon.
Ooh, please tell me it's not out of print. They should, or at least a version of it, yeah. Try SMPTE.org, and there's a store at SMPTE.org. If not, there may be a new edition coming out. There are several other good books out there, and in fact, I can probably put together a short list and forward it to the group if folks are interested. That's fine, I can do that. Yeah.
What tools, software are you using to convert born digital to motion JPEG 2000?
Well, first of all, there's no such thing as motion JPEG 2000. It's JPEG 2000, but that's another story. Right now, we're not using anything because the first system is waiting for the end of continuing resolution to be installed. However, we have had a proven and good experience so far with the tests that we've done with Radiant Grid, and we believe that they have a good JPEG 2000 lossless conversion module, and that is the first system that we are going to install and test full-time and actually put into production.
And I think this is the last one. How much quality are you really losing by compressing preservation 450 gig, for example?
Could you be a little more specific about what you're asking?
I'm just reading the question.
Could whoever said that send us an update? Because there's a lot of assumptions in that question.
Okay. And that's it. That's
Okay. There's no quick answer to the previous question because there are a lot of assumptions and I don't know what you're assuming by asking that question. However, if you follow up by email, I'll be happy to walk you through it. Okay, anybody else? That's it. Thank you for coming.
This has been a presentation of the Library of Congress. Visit us at loc.gov.